In this tutorial screencast, we're going to look at three separate reactions that achieve alpha halogenation of carbonyl-containing compounds. The first reaction we will examine is the acid-catalyzed halogenation. So if we consider the following substrate, we can see that it's a ketone, and it has an alpha carbon here and another alpha carbon, which we'll call alpha prime. So I want to point out the difference between the two. Alpha prime is called non-enolizable, and alpha is enolizable. The reason that alpha prime is non-enolizable is because it is not bearing any hydrogens. The alpha carbon has one hydrogen that can be enolized. So if we're taking this substrate with a single enolizable proton and treating it with trifluoroacetic acid and molecular bromine, what we are going to do is substitute the hydrogen that's been highlighted in green for a bromine atom. So again, the main concept in this module 3 is substitution at the alpha carbon. So how does this happen? Since we are under acidic conditions, we are going to generate an enol. And again, the enol is the nucleophile, the bromine is the electrophile. So our mechanism, as we've seen prior, is protonation of the oxygen of the carbonyl using HA. The carbonyl is now protonated through that proton transfer. Only the alpha carbon is enolizable. So at this point, the conjugate base of our starting acid is going to deprotonate. So we're ending up with the enol. So that's an alkene bearing an alcohol. This alkene alcohol, this enol, will then attack the bromine through collapse of the lone pair to reform the CO pi bond in the carbonyl. The alkene will then be nucleophilic at the alpha position, and then we cleave the bromine-bromine sigma bond. We have our protonated carbonyl. We've done our substitution. We have the bromide anion balancing out the charge. We can then show that being the conjugate base to abstract that acidic proton. And that's how we end up with our product, losing HBr. The next reaction we'll look at is the Hell-Volhard-Zelinski reaction, and this is the production of alpha-halo carboxylic acids that we can then transform into alpha amino acids and alpha hydroxy acids, which we've seen before in other modules. So say we're starting with butanoic acid. So in this case, for a carboxylic acid, again, we're at oxidation state 3. There's only one alpha carbon. That alpha carbon is bearing 2 hydrogens. And we know that the pKa of those alpha carbon hydrogens are between 20 to 25. So the reagents used for the HVZ reaction are typically elemental phosphorus and, say, molecular bromine. And then you do an aqueous workup, and that allows you to re-isolate the carboxylic acid. So again, the big picture of this module we have our alpha hydrogen identified with the green highlight. Now we have molecular bromine as the electrophile, so we're doing a substitution for H for bromine. We re-isolate the carboxylic acid. So there's our substitution, the alpha position. We know that bromine is a good leaving group. So we can take this molecule, treat with an excess of ammonia. That's going to allow us to synthesize an alpha amino acid. So we're going to show this as what we learned before, the Zwitter-ion. So that's a species that has both a plus and negative charge within the same molecule. The other byproduct is ammonium bromide. Again, we need to use an excess of that because the first equivalent of the ammonia is deprotonating the acid. The subsequent equivalent is then attacking the alpha position to do an SN2 reaction. So again, you've seen this mechanism before. That's SN2, displacement of a good leaving group with a good nucleophile. The last reaction that we'll learn for alpha halogenations is called the haloform reaction. And this isn't actually a traditional or classical test for methyl ketones. So if we have the following molecule, one way to name this would be methyl phenylketone. If we identify the alpha carbons, we have alpha and alpha prime, and you can see that the alpha prime carbon is not bearing any hydrogens, so we call it non-enolizable. So therefore, all the action is going to take place at the alpha carbon, which in this case has 3 hydrogens. The conditions for the haloform reaction, we're going to use an inorganic base such as potassium hydroxide. This is typically an excess. We're going to use a molecular halogen, so we'll demonstrate that with iodine. Again, this is an excess. And then finally, an aqueous acidic workup. The product of this reaction is twofold. We're going to end up with an acid plus the haloform. In this case, this molecule is called iodoform. And specifically with iodoform, it precipitates out of the reaction as a solid. So a few things to point out before we look at the mechanism of how this occurs. I'm going to write this carbon here in blue. Again, that alpha carbon has 3 hydrogens. You can see that in the acid product, we are missing that carbon. That carbon actually ends up here in the haloform. So we want to understand through the mechanism how we break the carbon-carbon bond between the alpha carbon and the carbonyl carbon. Because we are under basic conditions, we're forming the enolate as the nucleophile. So here is our methylphenyl ketone. And again, the haloform reaction is specific for methyl ketones only. You have to have a methyl group. So we have the alpha carbon. We know that those CH bonds are acidic. We have potassium hydroxide. That's a base. The base is abstracting a proton from the alpha carbon. That's depositing the negative charge on the alpha carbon. We have our potassium counterion. We're losing that conjugate acid of water in the process. The resonance form of this has the negative charge delocalized onto the oxygen. So this is what we typically think of as an enolate. Again, we have an alkene bearing a negatively charged oxygen, so that's the olate, enolate. We're then reacting that with the electrophile, which is iodine. We reform the CO pi bond. We're breaking the CC pi bond to substitute at the alpha position. So again, let me highlight that's the substitution that we have just shown to take place, H for I. Now what this does is, by substituting that halogen there, we've now increased the acidity of the remaining 2 CH bonds. So because we're using excess base and iodine under these conditions, that happens 2 more times. So each hydrogen is substituted for iodine. And again, each iodine is electron withdrawing, so it's increasing the acidity of the remaining CH bonds. If we plug in our lone pairs, we can now look at partial positive, partial negative charges. Each iodine is delta minus. So the carbon we can think of as delta plus plus plus. So what that is doing is withdrawing electron density from that CC sigma bond, and because we are in the presence of excess sodium hydroxide, this next reaction is a nucleophilic acyl substitution. So again, we've seen that mechanism before. We have a nucleophile adding to the carbonyl. We generate a tetrahedral intermediate. Again, it's always good to keep track of your lone pairs of electrons, your formal charges. Just going to abbreviate that Ci3. So that's the nucleophilic addition. Now the substitution happens through the collapse and reformation of the carbonyl. We're going to eject the Ci3 group. We form an acid. We have this negatively charged carbanion balanced out by the positive potassium. That carbanion is looking for an acid to deprotonate, which we've just formed. So at this point, as the reaction proceeds, is when you will see the haloform fall out of solution. So we have the potassium benzoate plus the haloform. And this is the reason why you need to add acid at the end, is so you can get the neutral carboxylic acid as the final product. And again, that's just a proton transfer. Again, that material precipitates out. So the reason this is a classical reaction in organic chemistry is that if you have an unknown substrate and you wanted to determine if there was a methyl group, you could run this and see if the iodoform precipitated out. So this has been a tutorial screencast examining alpha halogenation reactions under acidic conditions, Hell-Volhard-Zelinski reaction, and finally the haloform reaction.